Okay, we're continuing with more example problems involving rational exponents and the corresponding the radicals that correspond to rational exponents. In this video, we're going to work problems where we simplify rational exponent and radical expressions. So overall, this is pretty straightforward, except there can be some confusion in regards to when we're simplifying radical expressions, because there's the case where you've got if you have the nth root of x to the n and n is even, then we know that this is the absolute value of x, not just x itself. Because like you can't have, this is not equal to, because if we just said that this was equal to x, then that would be implying that this is minus 5, and that's not true, right? It's the absolute value of x. So this can create confusion whenever we are simplifying radical expressions. Okay, but we'll work some examples here and get a feel for how to work problems with it when this property is applicable. Now, there's also a little bit of confusion in the sense that, well, what if we started off with something like this? We're given this, right? How do you simplify this? Well, n over n is 1, and x to the first is just x, okay? But like, isn't x to the n over n, if we write that in radical form? Yeah, it absolutely is. This is correct per the radical form definition. Well, the nth root of x to the n is just x, not absolute value of x. Well, this is where you have to look at where you're going to learn this as you progress through algebra, but you have to look at the context of the problem. And the context, if we're given this to start with, then that implies the absolute value of x. But if we're given this to start with, then that implies just x. You can think of it like kind of like order of operations. You would if you started here, then the first thing you do is simplify the exponent, right? And then go from there. If you start here, it's the order of operations is different. That's one way of looking at it, but there's other ways. You're going to see as we progress through algebra, you're going to see, like with equations and whatnot, it makes a difference on what you're given to start with in the problem versus what you get as you simplify. Those contexts are different. So I'm not going to get into this too much here. You just need to, at the moment, just trust that this is true. If you start off with this, the nth root of x to the n, and n is even, then that's equal to the absolute value of x. But if you started off with x to the n over n, where n is even, then that's just equal to x. You just have to trust that that's true, and as you progress through the course, you'll get a feel for why this is the case. When you get through chapters 1, 2, 3, etc., you'll look back at this and say, okay, I get it now. Okay, and now also before we get started, we want to think about how do complex numbers come into play here, because again, you can look at any variable, x or a. Well, usually a represents a specific number, but this number could be a complex number. X could be a placeholder to represent not just any real number, but any complex number. All right, and so prior to rational exponents, we could talk about like adding, subtracting, multiplying, dividing, taking just positive integer powers. We talked about how once we learn more about complex numbers, specifically in trigonometry, we'll be able to extend all of these operations to complex numbers, no problem. So when you see just x by itself, and maybe you're multiplying it with another variable or dividing it, whatever, or x to a positive integer power, you can really start to think about, okay, that could potentially be a placeholder for any number, not just a real number. However, as I mentioned in the textbook section on rational exponents, because a rational exponent is associated with a radical, and at this point, through all of algebra and even into trigonometry, before we get to complex analysis, we don't want to be mixing radicals with complex numbers, except for the one special case where you've got a principal square root with a negative number underneath. Then we're going to learn how we can simplify that using an imaginary number. But other than that, we're not going to be mixing principal roots with radicals. And so with rational exponents, there's principal nth roots all over the place. Then for any time in all of this algebra course, so including this section, this video, if we've got a variable with a rational exponent, then we're thinking about that variable is going to be some real number. It's a placeholder for some real number. We're not going to be thinking about that as potentially being a complex number. Only if you have an x by itself or an x to some positive integer or negative integer as well, since like x to the negative n is, still just 1 over x to the n. So you could think about that as well. Those are the only times when you can think about, well, x could be a placeholder potentially for any complex number. But once you get to rational exponents, we're not going there. Anytime you have a variable to a rational exponent power, you're going to be assuming that variable is a real number. So now let's simplify this. Now the key to when it comes to simplifying expressions like this is remember that all of the properties of exponents that we learned when working with integer exponents extend no problem to rational exponents. So like a to the 2/3 times a to the 5/3, that's a to the m times a to the n. Well, that we know that's just a to the m plus n. When we worked with integers, well, that's no problem with rational exponents either. So what is 2/3 plus 5/3? That's 7/3. Okay. Now, what is 7/3 minus 1/3? That's going to be 6/3. 6 divided by 3 is 2. Okay, here you consider this it's not simplified because you'd rather have positive exponents if all possible. So that's easy. We just flip these, right? Take their reciprocals. And you consider that's more simplified. You can't do anything from there. You have two different, W and Y are different, but that's more simplified. Okay, same idea in that just because we have rational exponents doesn't mean that we can't apply the properties of exponents. We know we can write this because we know that like a times b times c to the n power is a to the n, b to the n, c to the n, right? So we can just write this as 16 to the 3/4 x to the minus 8 to the 3/4 y to the 1/5 to the 3/4, and then we apply the properties of exponents again. So this is going to be x to the minus 8 times 3/4 power, right? But okay, let's simplify this. So 16, the 4th root of 16 cubed, the 4th root of 16 is 2. There we go. So 8 times x to the minus 8 times 3/4 is minus 6 times y to the, so 1/5 times 3/4 is 3 over 20. So, okay, we've got 8y to the 3 over 20 like that. Okay, so let's see. We know that if you have like a over b to the n, that's a to the n over b to the n, and that applies with rational exponents, no problem. So we've got 2 to the 12 times m to the 2/3 times 12 would be what? 2/3 times 12 is 8. Okay, now n to the 3/4 times 12 is 9. Okay, n to the 1/5 times 10 is n squared. Then you've got 2 to the 10, m to the 1/2 times 10 is m to the 5th. So, okay, we're left with 2 squared. Here we're left with m cubed. Here we're left with n to the 7th. So 2 squared is 4, m cubed over n to the 7th. I think that's it. Yeah, there we go. That's 4m cubed over n to the 7th. Okay, here, to fix this minus 1 exponent, that's easy. Just flip take the reciprocal of this, done. Okay, now distributing this kind of, I don't want to call it distributing, but like, so m squared, m to the 2 times 1/2 power is going to be just m, and then you've got m plus n to the 1/2. Okay, so this is m to the first. So what we've got is 1 minus 1/2 is 1/2, and then we've got that. So m plus n to the 1/2 over m. Okay, so yeah, here we go. We've got the principal square root of y squared. So the principal nth root of a variable to the n power where n is even. So we know this is going to be equal to the absolute value of y, not just y. Because we're allowed to input a negative y here. Y can be anything here. One of the keys to simplifying radicals, but at the same time considering if you have to use an absolute value like this, is thinking about, okay, what am I allowed to input into what variables am I allowed to input? What I mean by that is we can't have a negative number inside of a radical with an even index. So you have to think about that. But here, y can be anything, though, because we're going to be squaring it. And so there's never going to be a negative number inside of the index. And so you might be thinking, well, okay, but then if we're going to be squaring it, then why do we need the absolute value? You have to look at it this way. So, okay, yeah, so if y was, let's say, -5, right, then we don't want to put -5, which would be just y. We want to put 5. We want to put the absolute value of y. You have to think about it. It's kind of like with a computer program. If maybe you were doing this in Excel or MATLAB or something. If someone can input something into a cell and input a value. But they can input, in this case, they can input any value they want. There's not going to be an error. They can input any value they want, any y value they want. Now, what's going to be output to them then? Once they input something, what's going to be output to them? You have to put the output. Like in Excel, you can specify the output is going to be, and you could just click, okay, whatever they put into the cell, right? Which would just be y. Well, you don't want to do that because if they input -5, that's not going to give an error. That's fine. But you don't want to just put this as the output because then it's going to give -5, and that's incorrect. You have to put the absolute value, ABS, of y. That's what you'd put in Excel, you see? Okay, now here we've got the nth root of something to the n, a variable to the n, but the index is odd. So this is just going to be what you would think it is. It's like y to the 3/3, which is just y. Okay, here we've got this still is the nth root of a variable to the n. It's just more confusing. Like you can think about this, if a is equal to 2x minus 5, then you've got the principal fourth root of a to the 4th, which this is going to be the absolute value of a, right? So this is going to be the absolute value of 2x minus 5. And the way you think about this is it's like, okay, it's going to be helpful to look at these problems, these when you're simplifying radicals, and think about what are all the acceptable variables that I could input. So like, what are all the acceptable x's that I could input? And what we're asking there is, are there any x values that are going to make this radical negative under this even root radical? And there are none. There are none, right? You can input any x, and because we're taking it to the 4th power, it's going to be, the radical is going to be positive. So you can input any x you want. However, we don't want to, we know that if there's going to be some x values, they're going to make 2x minus 5 negative. It's not necessarily negative x values because it's this whole expression, but like I guess it would be, so when x is greater than, or no, when x is less than 5/2, you get a negative. 2x minus 5 would be negative, right? If x was less than 5/2, you'd have 2 times 5/2 is 5. You'd have something, this 2x minus 5 would be negative. But it doesn't matter, though, because you're going to be taking it to the 4th power. And so what you don't want to do, though, is you don't want to have, if you left off the absolute value, then for the x's where x was less than 5/2, you get a negative value out here, and you don't want that. You can't have a negative value coming out of an even principal root, an even index principal root, right? So you have to put that absolute value. Okay, so here we're going to simplify this using the product property of radicals. So if you have the nth root of a times b, we know that that's equal to the nth root of a times the nth root of b. And all we do with that, we don't have to write all this out every time, but this just gives you a sense of what we're doing here. Is so, like in general, we could do so. Once we understand this property, we have the index of 2. 12 divided by 2 is 6, so w to the 6th. Okay, that's what we would do in general. However, we also need to consider that this is an even index radical. And so that there's an absolute value to think about here as well. So, but all right, we know that we can write this as the principal root of w. Well, let me do this first. We can write this as w squared times w squared times w squared times w squared times w squared. And then one more. That's 6. Okay, right? That's completely valid. And then we know with this product property, we can separate this out. Okay, and now we just, okay, what is the principal square root of w squared? Well, we know that that is the absolute value of w. Okay, now, so I'm going to write this out here. Okay, but one thing to note, though, let's say hypothetically that this problem was actually like w to the 11th. Okay, the principal square root of w to the 11th. Okay, well, it'd be similar. We'd have w squared times 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 w to the 1st, right? So we separate all that out, and so do we get the same thing, the absolute value of w? I mean, yeah, we do, but in that case, we don't have to put the absolute values. Why is that? Because if we had the principal root of w to the 11th, we look at the problem to start with and realize that we can't have a negative w anyway. So if w can't be negative, then you don't need the absolute values. That's going to be the key, one of the keys to simplifying radicals is you look at the original radical and you think about, okay, what can I input here? W can't be negative because w to the 11th can be negative. You can't have a negative under an even root radical. W to the 12th, w can be negative because it's going to be positive anyway once you take it to the even power. Okay, now the next thing to consider is that, okay, so we can simplify this. We've got to the 6th, right? So are we done here? Well, no, because if you take, we don't need the absolute value since we're taking this. If this was an odd number if we had an odd number of these, then we have to leave the absolute value. But since we have an even number, we can just take this off, the absolute value off, because the idea is if you have to think about it like someone inputs a w into the computer program. They input a w, and then what's the output going to be? Well, do you need the absolute value? Like if we just left this as w to the 6th, we don't need the absolute value because if w is negative, it's going to make it positive anyway. That's how you have to think about it. If somebody input a w, we know w can be positive or negative, like into Excel or MATLAB program that you made. Someone inputs a negative w, that's fine. And then we know the output's going to be take that value and raise it to the 6th power. Well, okay, you don't have to worry about the negative then because it's going to be positive anyway. So you just take off the absolute values. This is w to the 6th. Okay, yeah, here's a good example that. So we know we have to, and then, right, we can write it this way. So that's 3 absolute values of C. So don't we have to leave the absolute value? Well, no, c can't be negative anyway. We can't input a negative c into here with this even root radical. So it's just going to be c times c times c. So that's c cubed, like that. Now, in the future, to make this easier, you could just look at it like, okay, 6 divided by 2 is 3. You could do it like that. Okay, we've got a principal cube roots. There's no absolute values here. So we do d to the 9th times d squared. Okay, 9 divided by 3 is 3. And then we've got like that. Okay, now here there's no variables, so there's no absolute values that come into play here. We're dealing with actual numbers. So, okay, 6 times 4 is 24. So we've got 6 times 2 squared. So this is 2 root 6. Okay, let's see. 54 divided by 2. Okay, so 27 times 2, and then 3 cubed is 27. So we've got 3 cubed times 2. Okay, so you could take out a 3, and there we go. Okay, yeah, we've got variable terms here, but the index is odd, so we don't have to think about any absolute values. We can just do so. Okay, 250 is 125 times 2. That's 250. And then 5 cubed is 125. So we've got, let's see, 5 cubed times 2 times x squared times y to the 6th. We'll just leave that. And then times z to the 9th times z squared. Okay. So we could take out a 5. We could take out a y squared. We can take out a z cubed. And we're left with 2x squared z squared. Okay. Now here we've got an even index. So we have to think about the absolute value. Now, one thing to start with here is let's think about what are the what variables, like, okay, what can we input any q and any p? Well, we can input any p, but we can't input a negative q because it's raised to an odd exponent. So q can't be negative, so we don't have to consider like the absolute value of q or anything like that. Okay, so all right, what is, let's see, 96 should be divisible by 4. Yeah. So 96 is 24 times 4. That's 6 times 4 times 4. So that's 3 times 2 times 2 times 2 times 2 times 2. So it's 3 times 2 times 2 to the 4th. Okay, so let's see. We've got 6 times 2 to the 4th times, and then we're going to have p to the 12th times p squared times q to the 4th times q cubed. Like that. Is that right? Yeah. Okay, so we can take out a 2. Now, the 12 divided by 4 is 3. So, okay, but we know p could be negative, so do we need the absolute value? Okay, do we have like an even number? Are we going to have a p? We're taking out a p cubed, right? So that's odd. So yeah, we're going to need the absolute value. So what we're going to do is this. You could put the cubed on the inside or the outside of the absolute value. It could mean the same thing if you think about it, but I say put it on the inside like that. Okay, now next we're going to have just a q, and we don't have to put an absolute value. Okay, now let's see. We've got 6 p squared q cubed. Okay, let's see. So we've got 84, that should be divisible by 4. Okay, so 21 times 4, 7 times 3 times 4, 7 times 3 times 2 squared. All right, so 21 times 2 squared, and then we've got y minus 2 squared, and then y minus 2. Okay. Now, so do we need to consider, like, do we need to take out the absolute value of y minus 2? Well, no, because we've got a y minus 2 cubed here. So we can think about y is going to have to be greater than 2, or else you can have a negative underneath this radical. Well, if y is greater than 2, that means this is always positive anyway. So we just take out a y minus 2. Okay, here we can apply the quotient property. Okay, now, but we need to note, though, that with this even root radical, p can't be negative. So we don't have to think about any kind of absolute value needing to be taken out. So we know this could be 6. 6 divided by 2 is 3, so p cubed. There we go. Okay, let's see. We've got 4 times, and then we can do, so w cubed times z cubed times z squared, and then like that. And so we can take out a w and a z. Okay. There we go. Okay, here we can apply the quotient property in reverse. Okay, so we've got, let's see, 5 divided by, or 625 divided by 5 is going to be 125, I believe. Okay, so now we've got, okay, so x cubed over 125y cubed. So now we can go back the other direction and do this. Well, 125 we know is 5 cubed. Okay, so we've got x over 5y.